Sounds good.
Okay,
Maybe I'll do full screen here.
cool. Welcome everyone. We have Tim Tribone from Syracuse University today, and he's going to tell us how to do matrix factorizations with more than two factors.
Awesome. Thank you very much, Oscar, and thanks to the other organizers. I'm very excited to be here and get to talk to you guys about matrix factorizations. So the plan is to talk a little bit about just the basics of matrix factorizations, the original theory done by Eisenbud, and then I want to talk about Canara periodicity, whatever that is, and then I will get to these factorizations which have more than two factors possibly. Okay. So for anyone not familiar, I just want to start with a really sort of simple example of what a matrix factorization is and just give a flavor of the type of things that are going on here. So if you have a polynomial, this guy xy plus uv, so he's irreducible. But if we take a look at the 2 by 2 matrix with this polynomial down the diagonal, even though the polynomial can't be factored, this sort of can be factored. And in terms of these two matrices here, this is a nice little trick that you can do to get this identity times the polynomial factored. So this is maybe not that sophisticated and has probably been known, this sort of trick, by possibly many people, but Eisenbud in 1980 was sort of the first person to recognize the homological and commutative algebra consequences of these type of factorizations. So let's do maybe a little bit more formal definition, but I want to talk about the insights that Eisenbud had a little bit and then move on from there. So the context I'm going to do is starting with a regular local ring, and F is some element in there, although I'm constantly thinking power series ring and polynomial, really, honestly, but this guy should be non-zero. And then a matrix factorization of F is a pair of square matrices, just as we saw above, such that their product is a diagonal matrix with this polynomial F down the diagonal. And either as a definition or maybe as a quick lemma afterwards, you also want the other composition or product in the other order is also F times the identity. So you have phi psi is, sorry, go ahead.
Yeah, do we insist that matrices are always squared?
Mm-hmm. Yes, so if I didn't say that, it's an important point. So we want two matrices of the same size, and there's a little bit of an order of how you define these things. But if you insist that both products are F times the identity, then yeah, they need to be square. And we're not going to really think about any that are not square. So yes, good question. Okay, and so this is the basic definition. Eisenbud does it slightly different, more general context, but I really want a regular local ring, and even secretly, for most of what I'm going to say, it should be a complete regular local ring. But for now, this is good. So I said there's going to be some homological consequences. This is going to involve modules over the hypersurface ring defined by F. So I'm going to set that as R. And then also, just as notation, I'm going to call the category of these things matrix factorizations, or just the collection of all of them for a given F to be this capital MF of F. Okay. So how are modules getting involved? Well, if you have a factorization of F, so phi psi, their product is F times the identity, then the ring is regular. So it's in particular, it's a domain. And so this element, this non-zero element is a non-zero divisor. And it's not hard to see that that means both these maps have to be actually injective. And so you get a short exact sequence as presented here. And so the module that we're going to be looking at is the co-kernel of phi, as I've displayed here, but also the co-kernel of psi is important as well. So this is an S module. Why is it also an R module over the hypersurface? Well, F times anything in, I'm thinking of the middle term here. Well, F is phi times psi. And so F times anything in the middle term is in the image of phi. In particular, F is going to kill the co-kernel. when you mod out by that image. In other words, the co-kernel phi is an R module. And similarly for the co-kernel side, because both products are F times the identity. So we're getting R modules from these matrix factorizations. And actually, more specifically, they're a very special type of R module. They're what are called maximal Macaulay modules. And I'll sort of remind you of the definition of that on this next slide here. So a finitely generated module over a local ring A is called maximal Macaulay if its depth is the maximal possible value, which is the dimension of the ring. If this term is not familiar to you, I'm not actually going to say anything more about it, but let me cheat a tiny bit and just say it's a numerical invariant of the module, which is related to the projective dimension by the formula below, right here, which is the Auslander-Buchsbaum formula. And it says that if you have a module of finite projective dimension, then the depth of that module is given by the difference between the depth of the ring and the projective dimension of the module. Okay, so if you know depth, then cool. And if not, then what does this mean for us? Well, in this talk, because we're working over a hypersurface, this is going to mean that a module is maximal Macaulay over R, if and only if it has projective dimension 1 over the over S, the starting ring. And well, less than or equal to 1, but we'll sort of avoid free modules for the time being. So if you think back to the previous slide, there was this short exact sequence phi, and then going on to the co-kernel of phi. And so M that we displayed above precisely has projective dimension 1. And so what happens when you put these together is that when you have a matrix factorization, the co-kernels both have projective dimension 1. In other words, they are maximal Macaulay R modules. So this is a special class of modules that is really the only, the main class of modules that I'm interested in. But maybe if you're not interested or don't know about them, why should you care? Well, I'll try to give a little bit more insight on why matrix factorizations are still useful, even if you don't talk about maximal Macaulay modules, but we'll get there in a second. Okay, so far, if you have a matrix factorization, both co-kernels are MCM R modules. And it goes the other way. If you have a maximal Macaulay R module, by that formula that we just looked at, the Auslander-Buchsbaum formula, it's going to have projective dimension 1 over S. So you get a short exact sequence looking very similar to what we had before, but it's top row. And because M is starting life off as an R module, multiplication by F on this complex, or this resolution, is going to be homotopy to 0. And what this is going to mean at the end of the day is that, you're going to get a homotopy going back the other way. All of these are SN, so which way doesn't matter. But anyway, you get a map that's going backwards, and in particular, you get a map that does phi composed with psi is F times the identity. And it's not hard to check that the other composition also works. So psi phi is also going to be F times the identity on SN. In other words, these maps are going to make up a matrix factorization, maybe after you pick bases and make the matrices, or just think of them as homomorphisms, either way. Okay, so if we have matrix factorization, we get MCMR modules, and reverse, if we have MCMR modules, we get a matrix factorization, excuse me. And this is really what we've just done is outlined a theorem by Eisenbud in this original paper in 1980, which gives a correspondence, this correspondence between matrix factorizations and MCMR modules. And a little bit more specifically, you actually get a bijection between the reduced matrix factorizations, so that's a word I haven't defined yet, but I'll explain in a second, up to some very natural equivalence, and MCMR modules with no free sum ends. You get a bijection between these two classes of objects. Better than that, you get a stable equivalence of their categories, but I won't say much about that. Okay, so this is the sort of starting point for Eisenbud. Recognize this this bijection, and then goes on from there. What does this word reduced mean? We should talk about this. So for any F, any polynomial or just ring element F, you always have two very simple, trivial sort of factorizations. You could do f comma 1. So these are ring elements. This is the 1 in the ring. And so we're thinking this is like a 1-by-1 matrix factorization. And then you could also do the shift of this, the flip 1 comma f. These always exist, and the modules that they correspond to, remember, and we're taking the co-kernel of the first one. I should have mentioned you're corresponding the matrix factorization with one of the co-kernels. You could pick either one, but Eisenbud picks the first one, so we'll continue on with that. So if you have these trivial ones, what does this first one correspond to? Well, the co-kernel of multiplication by f is the hypersurface R, and the co-kernel of 1 is 0. So these reduced ones are going to be the matrix factorizations which avoid these two trivial ideas. So they're going to have no summands which are isomorphic to either of those. On the module side, that's going to mean you don't have any free summands. Okay, and if that was all kind of weird, this is equivalently the same way as just thinking these two matrices should have no unit entries to be reduced. Okay, so like I was saying before, maybe if you don't care about Maximal Macaulay modules so much, why are these things still useful for understanding hypersurface rings? Well, they're going to give us resolutions over R. So if you have a matrix factorization, this is sort of a picture of that composition that I was writing down. Phi composed with psi is f times the identity. And this is perfectly set up for if you kill f, tensor with the hypersurface, which I'm denoting here by bars, then phi bar times psi bar becomes 0. So this is a complex. And in fact, if you continue it on sort of periodically in either direction indefinitely, you have this long repeating complex of R modules, free R modules. But even better, it's not hard to show that this is actually, it's exact at each spot. So this actually builds a resolution of either of the co-kernels, depending on where you truncate it. But for example, if you truncate it here, you're getting a resolution over R of the co-kernel of phi. That's Maximal Macaulay R. Even better, again, all things that Eisenbud wrote down, is that if you start with a reduced matrix factorization, then this is actually the minimal free resolution of the co-kernel. So this is great. And one step further, I'm going to have to talk about or say one thing about depth again, but one step further than this is the really cool theorem, again, due to Eisenbud in the same paper, is that the minimal free resolution of any finitely generated R module, so now drop the Maximal Macaulay assumption, is, okay, so it's not periodic the way this one was, but it's eventually periodic. And with period 2, and the periodic part of the free resolution is given by matrix factorization. So why does this work? Well, it turns out if you go far enough back in a free resolution for any old module, you're going to start getting Maximal Macaulay modules. And from there on, you can get a matrix factorization to give you the rest of the resolution. But eventually, these things become too periodic. And there's even a converse to this statement, which I won't say anything about, but having periodic resolutions, it sort of characterizes hypersurfaces too. Okay, so just checking the time. So I want to talk about what Knorr did now. So yeah, so we'll try to work up to Knorr's periodicity theorem. We're not going to state the whole thing, but we'll sort of give the flavor of it and maybe the first part. And to do that, we first have to talk about a construction, which was due to Knorr, but also in the way I'm writing it is due to Yoshino as well. So what this construction does is it takes a matrix factorization of two different polynomials, and you should really do them in distinct sets of variables. So you have a polynomial f and another one g. You have a matrix factorization of the first guy and then another matrix factorization, phi prime, psi prime of the second guy. You can piece these together and get a new factorization, but now of the sum of these two polynomials. So the formula looks like this. anyone looking closely might be a little upset at me because this doesn't really work, but you do some clever tensoring with block identity matrices and it will work. But I've just admitted that because it makes it look kind of messy. But this is the general idea. And when you have 1-by-1 matrix factorizations, it'll work really nicely. What I wanted to say was this is great for sort of inductive arguments because you can work up the number of terms of a given polynomial. You can sort of get matrix factorizations for each piece and build up inductively because of this. So you have this new formula. Yoshino calls it the tensor product of matrix factorizations and denotes it with this tensor with a hat. He has a really cool paper called Tensor Product of Matrix Factorizations, which he does a lot of really interesting things for this. And my understanding, sort of intuition of why he's calling it the tensor product is because importantly, so let me say this in 2 steps. So I think it's called the tensor product because it has lots of nice functorial properties which behave like tensor products of modules. But it is important to mention that this construction has nothing to do with the tensor product of Maximal Macaulay R modules. So for example, if you took the co-kernel of phi and the co-kernel of phi prime and tensored them together over some ring in both sets of variables, it's not going to have anything to do with the co-kernel of this first map here. So just as a warning. Okay, so if this is a little cryptic, let's just look at the example that we did at the beginning that I cooked up very easily. The way I cooked it up super easily is that this really is just a tensor product in the form given by Yoshino. So we have a matrix factorization of x times y, another matrix factorization of u times v. You piece them together to get this formula, and that's a matrix factorization of the sum, x times y plus u times v. So you get to combine the two and get a matrix factorization of the sum. Awesome. Okay, so what we need to do for Knorr periodicity is look at a special case of this. And this is really the factorization that Knorr wrote down originally. So now we're going to look at we're start with a fixed f that we're interested in. And now we're going to add on z squared and get a matrix factorization of f plus z squared. So the tensoring thing allows us to do this very easily. If we have phi psi as a matrix factorization of f, then I can tensor with the only sort of interesting matrix factorization of z squared, which is z comma z. This is the formula that you will get. And so this is giving us a nice machine to go from matrix factorizations of f to f plus z squared. And this is this new polynomial that is related to f, but has this new term added on, is like sort of the key, the essence of the Knorr's results. So over the two, so as modules, what do these correspond to? Well, R is the hypersurface that we started with. There's a new ring floating around here. So f plus z squared defines a hypersurface like this. You add on a new variable and then mod out by f plus z squared. This thing I denote as R with a hash. Sometimes I'll call it R sharp or R hash. It's called the double branched cover of R for geometric reasons that I honestly don't know much about, but that's what it's classically called. And on the level of modules, what does this correspond to? Well, you start with the co-kernel of phi as an MCM R module, and then you look at the co-kernel of this first matrix here. It turns out that this is actually the co-kernel of this matrix is isomorphic to the first syzygy of the co-kernel of phi, but as an R sharp module. So we have a map going backwards from R sharp to R by just killing Z. And if you look at the first syzygy of R sharp, or sorry, the first syzygy of the co-kernel of phi over R sharp, it's isomorphic to this, this first matrix here. So this is the basic setup for what Knorr does. And so, so I already mentioned there's a functor going backwards on the rings, but there's also, for matrix factorizations, if you start with the matrix factorization of f plus z squared, you can get one of f by killing z. And so what Knorr does is looks at the composition of these two functors. So what I mean is if you take a matrix factorization of phi psi, you tensor it with ZZ, that same guy from before, and then bar here, I'm indicating you kill Z afterwards. So you go up to F plus Z squared, and then you come back down to F. What comes out is phi psi direct sum, its sort of shift, psi phi. I call this the shift for reasons that we might get to later. And then what's interesting is that if you do it the other way, so this can be, the first one can be seen kind of easily from the formula that I gave on the previous slide. But the other way is also interesting. If you start with a matrix factorization of F plus Z squared, you kill Z, and then you tensor it back up to a matrix factorization of F plus Z squared again, you get the same sort of phenomenon. You get the one you started with plus its switch, psi, and then phi. And so Knorr's first big insight is what this tells you. You have to, with a little bit of care in thinking about it, what this tells you is that you only have finitely many indecomposable matrix factorizations of F if and only if F plus Z squared has the same property. So you're getting this sort of representation theoretic statement about matrix factorizations of F and of F plus Z squared. So you can only have finitely many indecomposable ones, non-isomorphic, if and only if the same is true of F plus Z squared. Okay, and this is a big portion of Knorr's global periodicity theorem, or the whole sort of program. But the next step of the periodicity is you do this process again. You sort of add on another variable plus W squared or something like this. And in that case, you get even stronger results. But I'm not going to say anything about that, unfortunately, but this sort of first step is what I want to focus on. And the whole paper due to Knorr, as well as another paper, what they eventually lead to is the complete classification of hypersurface rings of what's called finite Cohen-Macaulay representation type. So what I mean by this FCMT is you have a hypersurface, finite Cohen-Macaulay representation type means you have only finitely many non-isomorphic indecomposable maximal Cohen-Macaulay orthogonals. It's a mouthful, but that's what it is. And between the two papers, they totally classify them. And if these words mean anything to you, really what it turns out to be, there are assumptions here. You need algebraically closed and characteristic zero and some other things, but I'll avoid that for now. And what it turns out to be is that this hypersurface is finite Cohen-Macaulay type, if and only if you have an ADE singularity. So if that doesn't mean anything to you, I'm not going to talk any more about it. But if it does, this is like a huge, major theorem, and it's really cool to connect back to these ADE singularities. All right. So a key ingredient of this Knorr's periodicity in general, and also the three results that I was sort of listing on the previous page, is actually a non-commutative ring. So you have the double branch cover is the ring we defined like 2 slides ago or so. So the R is the hypersurface ring, still defined by F, and then the double branch cover is the one where you add on a new variable Z and then mod out by F plus Z squared. And then the non-commutative part comes actually from you're saying R hash bracket sigma, and sigma is a automorphism of the double branch cover. So this construction is called the skew group algebra. It's not too different from like a group algebra, except there's a twist in the multiplication. So you have this automorphism of R sharp. It's going to fix S, thinking of that as sort of like our base ring here, fixes S, and it's going to send Z to minus C. And this defines an automorphism of R sharp. And this algebra is a key component to what Knorr does. So let me just say a few things about it. So first of all, it has elements of this form, like kind of like a group algebra. It's coefficients from R sharp, and then you have the formal multiplication with sigma. And you can multiply sigma on the left of an element of R sharp, but you have to pay the price of evaluating sigma at this ring element to move it past. So this is the non-commutative part of it, and it's going to adjust z. It's going to affect z in this way, give you a minus z. And so what Knorr does is he gives an explicit equivalence of categories between matrix factorizations and MCM modules over this skew group algebra. So this is like an important starting point for the theory that he develops. Oh, what was I going to say? Oh, so sorry. MCM modules over a non-commutative ring. We didn't talk too much about MCM modules in the first place, but over a non-commutative ring, it's even a different thing. What should this mean? Well, it turns out the definition is you take R-sharp sigma modules, which are free over S. Those are the ones we're going to be looking at. So you have matrix factorizations on the left and a category of modules over some non-commutative ring on the right. Awesome. Okay, so up to this point, I think I've said what I want. So about Knorr, Knorr does a lot more leading up to the periodicity. This is sort of like an important first step. But identifying the matrix factorization with this module category is really kind of key. So that's all I wanted to say, actually. Okay, so with those results in mind, those specific ones, I want to move on to these factorizations, which might have more factors. So the definition to start is just sort of a natural generalization of matrix factorization. Instead of having a product of two matrices, phi times psi being f times the identity, now we're going to look at tuples of matrices, again, all square of the same size, so that the product, and you sort of have to pick which order to multiply them, but I'm going to say for the definition, this product is equal to f times the identity. So this is a d-fold factorization is what I'm calling this. And d here is going to be greater than or equal to 2. Excuse me. So this definition is not really new with me. I didn't come up with this, and it's been studied by a handful of others. I'll talk about a few specific examples. But the sort of working towards Knorr's periodicity, maybe for d-fold factorizations, is some of the new stuff. So what I want to do is talk about the category of matrix factorizations, which have d factors, d being bigger than or equal to 2, and I'm going to denote that as mf, now upper d of f. So some really basic examples to start. The first thing you can sort of do if you're thinking about these things is if you have a matrix factorization in the normal sort of Eisenbud sense with two factors, you can inflate it by just tacking on a bunch of identity matrices. And this is going to, depending on the number of ones you add in, this is going to be a d-fold, or whichever number you add, a d-fold factorization of that. So this is pretty uninteresting. Not much happens here, except for in one small case, which is when you have these really trivial ones that we talked about before. So for d equals 2, there was f1 and 1f. If I look at the 3 that are going to appear, for example, for threefold factorizations, f11, 1f1, and 11f. So again, these are 1-by-1 factorizations of f, but now with 3 factors. These are going to turn out to be important, but otherwise, these kind of adding on just identities is not very interesting. So the next thing you might ask is are there any interesting ones? And very naturally there are. If you have anything that's monomial degree 3, you can totally factor it. And even if you have, I'll give an example of irreducible things that have threefold factorizations too. So there are lots of really cool examples showing up in unexpected places. So this is a threefold factorization of x times y times z. You just throw in commas, x, comma, y, comma, z, 1-by-1 factorization of x, y, z. So I'll do more examples in a second, but sort of a reverse example, if that makes any sense. If you start with a d-fold factorization, you can always come back to matrix factorizations with 2 factors by sort of collapsing any number of maps. up to D minus one of them. So if I collapse phi2 up to phi D, think of this now as a 2 factorization, phi1, comma, phi2 multiplied by phi3 up to phi D. So we get.
Can I have a question at this
Absolutely. Yes, go ahead.
Because with 2 matrix factorizations, you had that commutativity, right? So what's going on here with the commutativity?
Yes. So great question. What turns out to be the case, you have to, there's a little bit of a choice at the very onset of which path you take. But with this path that I've taken, if you assert that you want all the matrices to be the same size, then it's not hard to show that the cyclic permutations of these guys are all f times the identity. So for example, phi2, phi3 up to phi D, and then multiplied by phi1 is also f times the identity. phi3 upwards of there. Yeah. So this is the idea. And that piece that you just mentioned, along with this bottom bullet, one sort of consequence of that is that the co-kernels of all these matrices are also going to be Maximal Macaulay R modules. This is an important part. Yes, thank you. That's a really excellent point. So you can either write the definition as I've done here, or you can insist from the onset that each cyclic permutation is f times the identity. It's just a lot more to write down. So I like to do this one. Yeah. Okay, thank you for that. And you could sort of see it in these 3 trivial ones. I mean, it's a very simple version, but they are really cyclic permutations of each other. Okay, so that last reverse example, collapsing a matrix factorization into a twofold, actually has an interesting correspondence with Maximal Macaulay modules. So if you have I'll stick to D equals 3 just for concreteness here. If you have a threefold factorization, phi1, phi2, phi3, you can write down a really nice commutative diagram where you have phi2 on the bottom going to the co-kernel of phi2, and then across the top is this collapsed version, phi2, phi3. And because you have an identity here in the middle, snake lemma gives you an extension of MCM R modules. All 3 of these are Maximal Macaulay R modules, and they fit nicely into this short exact sequence. And even better, kind of in a way, is that this middle module is actually isomorphic to the first syzygy of the co-kernel of phi1, too. So this is like an extension which is somehow involving all 3 of these maps together in some interesting way. And if you permute things, you can make other extensions as well. So the Maximal Macaulay modules are still lurking the whole time, but the exact relationship is a little bit more unclear with these default factorizations. Okay, how am I doing on time? Yes. So let me zoom through a couple examples because I don't want to go too long, but a really cool construction due to Blazer, Eisenbud, and Schreier will give default factorizations of homogeneous polynomials of degree D. So this example I've written down is a homogeneous polynomial of degree 3 xyz plus uvw. And so, sorry, let me slow it down a tiny bit. So we have this polynomial, it's homogeneous of degree 3, and it's going to be irreducible. And here is a zeta, which is going to be a primitive third root of unity. So if you kind of carefully place the primitive third root of unity and permute all the diagonals in just the right way, you get a matrix factorization of this sum xyz plus uvw, which I'm calling f. And this is really neat. And actually, it's like very much a direct extension of that tensor product formula that I gave earlier by Yoshino. And so I like to think of this as like a threefold tensor product. And what Blazer, Eisenbud, and Schreier do is they give it for default. You can sort of tensor a default factorization with another default factorization and get a default factorization of the sum. And so this is just, first of all, a cool example, but it also allows you to do the same sort of inductive iterating of tensoring these guys. And you can make any number of statements, one of which is what I've written here. If you have a polynomial, which is a sum of terms, each of which is degree at least D, then you can write down a reduced matrix factorization of F with D factors. And reduced here again just means no unit entries in the matrices. So these three authors were particularly interested in cases like this one, where you have all linear entries, because then the co-kernels of these matrices correspond to what are called Ulrich modules. I'm not going to say anything else about those, but that's the context they were interested. But you can sort of do it in a number. Their formulas work really sort of in a lot of generality. So it's really cool. Another really kind of unexpected place that these d-fold factorizations, in this case a threefold factorization, turn up is in the paper of Bookfights and Lusky, which says that if you have an n by n, so this is a specialization of what they do, but the statement I'm going to make is that if you have an n by n matrix over S, where n is even, and that's critical, then you can factor the adjoint of that matrix into a product y times z for some non-invertible matrices y and z. And so what this gives us is a triple factorization of the determinant of x. We should assume non-zero in the first place, but this is the idea. So you get a threefold factorization from their construction, and they do it in such generic terms that they give so many examples all at once, because what they actually do is they factor the adjoint of the generic matrix, and then you can specialize to whatever matrix you want from there. So this is a really cool paper. They do way more than just this. This is like a very specialized version of what they've done. But a tiny bit of backstory about this is that the question of whether this was possible was originally posed by Bergman, if you could factor the adjoint of the generic matrix. And in his paper, he actually shows you can't when n is odd. And somehow this involves invoking the Hairy sphere theorem, which is kind of wild to me and unexpected. And so he showed that you couldn't, and sort of conjectured whether you, when n was odd, and then conjectured whether you could or couldn't when n was even. And Bookfights and Lusky went and showed that you could whenever n is even, which is pretty wild. Probably bigger than equal to 4 or something like this as well. Okay, so with the remaining time, I want to talk about some of the things I've done and just hint towards where canonical periodicity could go for matrix factorizations with d factors. And so the first result I want to talk about, it looks really similar to the one that I wrote before, which is that there's an equivalence of categories between matrix factorizations, now with d factors, and a category of modules over r hash sigma. So it looks exactly the same, except the meanings have changed slightly. So let me explain that. So now d is bigger than or equal to 2, like I was saying. This will collapse onto Knorr's original result, so it works when d equals 2. Now r hash is no longer the double branch cover, but is what's sometimes called the d-fold branch cover. So you add on a new variable z, and then you mod out by f plus z to the d instead of z squared. Sigma is still has the same idea. It's an automorphism of the d-fold branch cover, which fixes s, but now it's going to have order d instead of order 2. The way I accomplish that is by going to get a primitive d-through unity, which are showing up a lot in all of this stuff, and sending z to omega z. So this defines the automorphism of R sharp and allows you to define the skew group algebra R sharp sigma, just as before, but now with this new context. And so it turns out those categories are equivalent. And I can even give you a little explanation of how this equivalence works, at least one direction, because I think it's kind of neat and it's rather intuitive. So if you have a MCM R hash sigma module, remember these are R hash sigma modules which are free over S. So this thing is naturally, I'm going to call it N here. This thing is naturally an R hash module because R hash sits inside of R hash sigma. So that's this first part. And then it's also a free S module just by definition. These are the modules we want to look at. And so if we go look at multiplication by Z on this R hash sigma module N, composition, and I'm going to call it phi here. So this phi is given by multiplication by Z. If I compose this map with itself D times, this is going to give me minus F times the identity on n. So it's multiplication by minus f. Why is this the case? Well, n is an R hash module and z to the d is minus f on R hash modules. So multiplication by z, d times gives you minus f. All right, well, we want a matrix factorization of f, not minus f. So a little bit of adjusting needs to be done. You have to do something to deal with the minus sign. Alternatively, you could have looked at f minus z to the d, but this is sort of what Knorr and Eisenbud, or well, what Knorr did, so I followed that. So you have to do something to adjust for the minus sign, but the point is this gives us a d-fold factorization, which looks approximately like phi d times. So phi, etc. And this is really the same sort of idea that Knorr does as well, but in the case d equals 2. And so, yes, so you do something to adjust for the minus sign, and now we get a matrix factorization with d factors. That's one direction of the equivalence, and the other direction is not too hard either. Oh, and the other thing I wanted to mention was that, so you send, the functor sends n to not quite this matrix factorization, but a summand of it. This thing sort of decomposes in a really symmetric way, and you pick a distinguished summand and send it to that. This is how it goes. And the decomposition is also interesting too. It's like a eigenvalue decomposition, basically. Okay, so sorry, jumping on there. This sets the stage for Knorr stuff and is really cool. I liked it a lot, but it maybe has one disadvantage, which is that I haven't mentioned, which is that all of this is characteristic dependent. You can't have, D needs to be a unit in your ring S. So in case that's an issue for you, I then, there's another result that I want to talk about, which is really inspired by Solberg's work, which is going to be characteristic independent. So I mentioned that the trivial factorizations were going to be important, and this is sort of what I meant by it. So if D is bigger than 2 again, we're going to let PI be the ith trivial D-fold factorization. So these are D tuples. Right now they're 1 by 1, just with elements in the ring. And the ith trivial one is going to be multiplication by f in the ith spot, and then 1s everywhere else. So it's the same kind of idea we had before, except now with full D-fold factorization. We then let gamma be the endomorphism ring in this category of matrix factorization of the direct sum of all of the trivial guys, P1 up to PD. And it turns out that the MCM modules over this ring is equivalent to matrix factorizations as well. Again, what does the maximal Macaulay modules over a non-commutative ring look like? It's again it's the gamma modules which are free over S. You can write down pretty explicit equivalence here. It's a little bit complicated and messy because you have these D tuples of matrices, but it's pretty cool. And so the slight advantages, I mean, I'm not claiming much, is that it is characteristic independent. And then also, before I mentioned that S really did need to be complete for a lot of the things I was saying, and here S doesn't have to be complete if it doesn't want to be. Okay. And one other thing that I just wanted to mention, which was particularly neat, I thought, was that if you do have the right characteristic and all the right assumptions, that these two approaches are really super closely related because these two rings are actually isomorphic. You can write down an explicit isomorphism, which does some cool sort of weighted averages back and forth. It was fun. They turn out to be isomorphic under the right assumptions of characteristic stuff. Okay. 50, doing pretty good. So one corollary of really either of these results is that the category of matrix factorization has projective resolutions because it's equivalent to this category of modules over these rings, and they have projective resolutions over there. So you can think about projective resolutions of matrix factorizations. In particular, you can ask, what is the syzygy of a matrix factorization? Just by the way, the projective objects in this category turn out to be exactly these trivial guys, and that's why everything is working out the way it is. You can do projective resolutions. They're just direct sums of copies of these projectives, or the trivials, sorry. So you can ask, what is the syzygy of a matrix factorization? Well, when D is equal to 2, maybe the reason it's not talked about too much is because nothing really, it's just the shift. I mean, this is important, but nothing unexpected happens. If you have the syzygy of phi psi, it's at precisely psi phi, or isomorphic to psi phi. As soon as you go bigger than 2, some unexpected things, at least unexpected to me, happen, which is that you can start with a reduced matrix factorization and the syzygy will not be reduced. It will have unit entries. So for example, if f is x times y times z, we can look at the factorization that we mentioned before, which is just x comma y comma z. So it's a 1-by-1 matrix factorization with 3 factors. It is reduced because all the entries are in the maximal ideal. The syzygy in this category is precisely this triple of matrices. And you can see each one has a 1. And this is weird. The reason it's especially weird is because it's not, these ones are not redundant in some way. So this matrix factorization, omega x, I'm calling it for the syzygy, is actually indecomposable, even though it's not reduced. So it has unit entries, but you can't sort of get rid of them if you wanted to. And such a thing does not happen in the case d equals 2, because if you have a unit entry in either matrix of a twofold factorization, then it automatically has a trivial summand. As soon as you go to d equals 3 or higher, this sort of weird thing where you get unit entries in very non-trivial factorizations showing up all the time, which is was kind of neat when I first came across this. So one other, let me think if there was anything else I wanted to say about this. Yes, okay, I think we're good. So another observation, so this syzygy in the category of matrix factorizations has like a very explicit formula you can write down. It's big tuples of matrices. But anyway, you can look directly at them and you can sort of observe that if you do this process twice, if you take a syzygy of the syzygy, you're going to get back to where you started, up to projective summands. You might have some trivial things laying around, but you will get back the original one where you started. And what this is going to tell you is that, sort of similar to what we had at the very beginning, this is going to allow you to build periodic resolutions over this non-commutative ring R hash sigma. Lets you go back and forth between the equivalences. So this is making it seem, you can write down a really similar statement to that theorem that I wrote of Eisenbud's, which says that if you have any module finally generated over R hash sigma, it's got a free resolution, which is eventually 2 periodic. And in one way or another, the periodic part is given by a matrix factorization. And this is a just property of this ring now. And on the other hand, you can do you can apply some classic Auslander results to find out that this ring has finite injective dimension as a module over itself, actually on both sides. And so the second one I'm thinking of is as it's saying something like this is a non-commutative Gorenstein ring, if that means anything to you. The injective dimension is finite. And so the way I'm thinking about this is if you piece these two together, you're saying something like this non-commutative ring is behaving just like a hypersurface homologically. It has periodic resolutions, at least eventually periodic, and it's got finite injective dimension. This makes it Gorenstein, and so those two combined makes this seem like a non-commutative hypersurface ring. And that's not a the only other thing I want to say is there's nothing else much to say about it, except that this really resembles the original theorem, which is that the category of matrix factorizations, which is equivalent to the category of MCM R hash sigma modules. So we found that matrix factorizations are equivalent to a module category over a hypersurface ring. Now, maybe non-commutative, but it's the same sort of flavor. And that's where I'll stop. So thank you very much for listening. If there's any questions, I'd be happy to answer.
Okay, so let's thank to Tim. That was a very good talk, and we usually do this by clapping or by reactions. So I will do both of them.
Thank you.
Hedda and Joy.
Awesome.
And then I know young people have different meanings to emojis these days, but I think these are pretty standard and good. Okay, any questions for Tim?
I have one.
Mm-hmm.
So I'm new to matrix factorizations and I'm trying to understand how they're used.
Mhm.
So in terms of like, I'm used to taking free resolutions of finitely generated modules. That's the world I live in. So when I have a matrix factorization, like what kind of modules I have, and does it say anything about free resolution of something? That was the two periodicity result. I can't
Yeah.
remember the statement of that one. What was it for?
Let me go back to this one. Yeah. So yeah, maybe I didn't emphasize the periodic part here, but what's going on is that of any matrix factorization is going to give you a two periodic resolution of this, the MCM R module. So wherever you truncate this, either at co-kernel of psi or co-kernel of phi, it's giving you a periodic resolution from there on of that module.
Okay. Thank
And
you.
so, yeah, so if you take any module and you go far enough back in a free resolution, eventually those modules are MCM because depth goes up as you go back in a free resolution. So then you could find a matrix factorization that gives you one of those syzygies and then finish the resolution in a periodic way afterwards. There's sort of a, oh, go ahead, sorry.
I had a related question. Like when you say syzygies of that, like a triple matrix factorization, like we had that example on page 20. What do we mean by the syzygy of that triple?
Yes, it's a great question. So this, the category of matrix factorizations is not abelian, kind of a little bit of a weird category, but it has what's called, if you're familiar, an exact structure on it. So you can have a replacement for short exact sequences, basically. And long story short, that replacement for exact sequences allows you to eventually build projective resolutions. There are projective objects with respect to this exact structure. And so when I mean a syzygy, I really mean the first syzygy. I mean map a projective onto my matrix factorization X in whatever way I'm allowed to do that, and then look at the kernel.
Mm-hmm.
Yeah. So there's big diagrams of lots of you can draw some big sort of ladder diagrams where this thing is showing up as a kernel of. That's kind of cryptic. I'll just end that statement there. But
that's okay.
It's kind of a weird thing. I didn't know anything about it until I started looking at these. But it's like a replacement for, if you don't have an abelian category, you look at these exact structures.
But from your theorem, it just means that you look at the co-kernel of this first matrix, well, co-kernel of X, right? And then you take the syzygy of that, and then the corresponding matrix factorization is this matrix factorization. Do I get it correctly?
Not quite, because the correspondence between bigger than two, so threefold or bigger factorizations, it doesn't work as well with the MCM R modules. There's not a one-to-one correspondence because there's some redundancies going on. So it's not bijection.
But if I just identify the free module, projective module with 0.
You still have to be a tiny bit careful going back and forth between threefold factorizations and MCMR modules. There's not a real good way to go back and forth that I understand yet. So this is really like a categorical syzygy, like totally almost separate from the. So let me try to re-answer the question. This syzygy of a matrix factorization is totally corresponding to the syzygy of the module over the non-commutative ring.
Oh, that's what I meant. Yeah.
Sorry, yes, that is absolutely right. Yep. Yes. So let me go back to either one of these. So the category of matrix factorizations is equivalent to this module category. And if you take a syzygy over here in the normal way, that will correspond to the syzygy on the other side also. That's totally how I should have answered it in the first place. Awesome.
Thanks.
I have a question, but it might be nonsense.
No worries, sure.
Some of the language you use sounds a bit similar to Auslander-Leiten theory language, and Auslander name already popped up once.
Yes.
Is there any connection?
Sorry, go ahead.
Yeah, no, is there any sort of parallels or tools of one theory that's applicable for the other?
Right. So I'm certainly have a sort of representation theoretic mindset in a way. I mean, not that I'm totally qualified for that mindset, but that's the way I'm thinking. So Knorr's result at the end of the day is talking about, classifying indecomposable module matrix factorizations and therefore modules. So I'm thinking about this sort of the same terms. So in that sense, definitely connected to representation theory and therefore Auslander-Writing sequences. And Solberg does show that the twofold category of matrix factorization has Auslander-Writing sequences in certain contexts. I think when you have an isolated singularity. I don't want to say that for sure. But I haven't actually worked with AR sequences at all so far. It's definitely on the to-do list to see if that sort of thing is possible, but it's not something I've tackled yet.
Also, you are working on square matrices, so that wouldn't be a short execution. Thank you.
Yeah, absolutely.
One thing I wanted to ask is this gamma is never of finite global dimension, right?
Only if these D are the only ones. If there's no other way to get a matrix factorization with D factors, then sorry, let me say it again. If the only matrix factorizations are the trivial ones, then it's going to be a finite global dimension, but otherwise it shouldn't. And that's just Auslander-y things, applying some, what should it be?
Okay, let's thank Tim again if there's no other questions.
Thank you, guys.
Normally what we do is we give we take some time to do some coffee break, chatting and talking, getting
Right.
each other. But I don't know if I think students are showing up.
That's no problem. And in the worst case, I can take them to a breakout room or so. But anyway, we usually don't start before 7:15, so it's okay.
Okay. And 7:15 is 12 minutes from now.
But we can always use the breakout room and so on. So don't worry.
Yeah. Okay. Breakout room and waiting room and everything else. Okay. Yeah. Okay. So this is it. This is the last talk that we had for the semester. So this is cool.
Awesome.
Really? The series is over?
We do not want to comment on it.
Very political. Great.
So,
okay, well, I have to leave for now to teach my class, but thank you to Tim and to all of you. Bye.
Thanks for coming.
I
So
have questions about this. So
sure.
I was telling Graham that I do not like the definition of maximal Macaulay modules as the ones which are free over S.
Oh, for a non-commutative ring?
Yeah. Instead, I was using the Gorenstein projectives as the definition of maximal Macaulay modules.
Gotcha.
And I told them that it doesn't matter in this case because your modules it's the same because it's like a Gorenstein order.
Right.
As the least injective dimension possible. And then he told me that This is good because then we do not have to fight over the definition and how I was wrong. So
Me and you.
I
You
took
mean-
I have a couple of papers that I have been writing forever now,
Hmm.
and in all of their introductions, I like spend a lot of time saying that in the non-competitive world, there are two types of Maximal Macaulay modules. They don't always agree, and then I took it to myself to convince Graham that he's wrong. So I started writing like a huge blog post about why Graham's wrong. At the end of the day, I convinced myself that your definition is correct.
Well, I'll say it's definitely not my definition, but I'll go with it. Yeah. So what's the context when they don't line up? If you're, because I'm like on a regular ring and it's a hypersurface, these are making things really easy. But
In the commutative world, they do agree. In the
Okay.
non-commutative world, they do usually not. So
okay.
one thing that you can look up is Joshua Stengel's PhD thesis. He talks
Yeah.
about these orders, right? And there you have this Auslander-Buchsbaum formula, not exactly an equality, but some inequalities.
Hmm.
So it is possible that you have modules which are Maximal Macaulay over the base ring. So let's say you have a regular ring, or maybe with a Macaulay ring given, and you have a non-commutative algebra over this ring, which is itself Maximal Macaulay,
Sure.
which is the case you are in.
Right.
You have a free module. Then it is possible that you have Maximal Macaulay modules over the base ring, which are of finite projective dimension, but which are not free or which aren't projective. And the maximum projective dimension available here is the projective dimension of the canonical module, which is defined as,
Yeah.
anyways, it's fine. And
Yeah. By some things. Yeah.
but it's like sort of the injective. It is related to the injective dimension of your algebra,
Gotcha.
computative algebra, and in this case, your injective dimension is the least possible. So
Right. Right. Maybe that has something to do with that. I mean, the other thing that makes me think of is the one setup, which is really by Solberg, is doesn't require the ring to be complete, the regular ring. But the other setup with the skew group algebra, you really need that the regular ring is complete because you need that the double branch cover is finally generated free over S. And that's not, I don't think it's true when you have I don't know why, but I don't think it's true when you have a non-complete. It can be not true when you have a non-complete ring. So there's a disconnect there too that I don't fully understand. But this is, it could have something to do with it also.
this is very cool. One thing I was wondering if
Mhm.
you know anything about Hochschild cohomology.
I do not. I really don't.
Me neither. So that's okay. Let's say goodbye for now. If
Okay.
I have questions, I will email you.
Yeah, sounds great.
It was a very good talk. Thank you. I really like your presentation.
Awesome. Thanks for inviting me and nice to meet you.
Bye bye. Nice to meet you.
Yeah, Alp as well.